good performance. Right, so we will try to design a good controller so that our controller performance is pretty good. So in this context, let us come back to that lift problem. What we require from our controller is there should be no overshoot. It should not take a long time. Okay, these two are main objectives. You can also add it must work from 0 to, let's say, 8 people in thick. So these are let's say our control objectives. So we are trying to design a lift which will go from one floor to another floor. Let's say the other floor is here. So it should go from here to here. It should not be so that it goes there, then does this, and then comes there. That should not be there. So it should not oscillate. It should steadily go there. Second thing is, it should not overshoot. It should not go and stay somewhere here. Or it should not undershoot. It should not stay somewhere here. It has to go and perfectly align with the floor. Otherwise, when the gate opens, people will fall down. Okay? So it must go and perfectly align. It should not oscillate like this. It should not overshoot or undershoot like this. And it should not take a very long time. It should not go like slowly, very slowly going, because you cannot overshoot. You go very slow and do like this. That will be irritating. If you have, let's say, 100-floor building and it's moving very slowly, even one floor, if it is moving very slowly, it will be irritating. So you have to reach the target in minimum time. You should not overshoot the target. You should have a zero steady state error. That means when you reach finally the controller stops, there should be no error. So these are principal goals of the controller. Now the problem is, how do we design this controller? So let's say one way is the lift manufacturer installs the lift, and the controller, some gains and some parameters are there. He is trying to tune them. So he opens the lift door, tells one person, please get in. Then he operates the lift and tries to control the gates so that it works properly. Then again he calls, okay, 3 people get in, please. Again it goes up and he readjusts the gain. Again 8 people get in, maximum people, maximum load. Again readjust the gain. So if that is the case, then the controller will change from people to people depending on load. Controller will change depending on height of the building. That's not the way things are done. What is done is, a controller must be such that it is robust. What does that mean by robust? Robust means controller should be able to automatically take whatever load comes on it. Let's say maximum allowable load is 500 kg. If 500 kg is exceeded, it can have a load cell on the cable and it will give a warning and stop. But 0 to 500 kg, whatever load you give, its performance should be safe. So controller should be robust. And we have to design a controller which should not depend on parameters of the system. So what we require from all these things? This controller should be robust. To design controller, we cannot always do trial and error experiment on the real system. So this controller, we cannot do experiment on the real system to design it. What we need the controller to be designed using a model of the system. This is very important. But that model of the system is important because we cannot do experiments on the real system at all times. First of all, it's not practical and it may not be feasible. For example, let's say you have a controller that will shut down the plant in case of a leakage. Let's say something like Bhopal gas tragedy that happened, some leakage happened. Suppose there were a controller which will shut down the plant. Then you cannot really do an experiment and allow gas to leak out and then check whether the controller is working or not. You have to simulate it. Likewise, if you look at today's world, even Indian context, we do not again and again carry out nuclear explosions. Whatever bombs we had to test, we have tested. Based on those test results, we have created models. And when we develop a new bomb, we are using that model to predict how much kilotons of explosive power will be delivered because of explosion of that bomb. It's not feasible that we always go and test a bomb somewhere in, let's say, Rajasthan or somewhere in the sea. That's not feasible. Likewise, many things cannot be actually done in practice. We have to create models and simulate those. So, controllers, especially for safety critical systems, such as accidents, avoidance, or so on, we have to develop those based on models of the system, not on the DLC. Still, in some cases, you can include the real system. There are various ways of doing that. So the levels of controller development can be classified as software in the loop simulation or SILS. What's there? In this, the controller is a software. You don't have actual controller. The controller is, let's say, in MATLAB. Controller is in your computer. Controller is, let's say, in LabVIEW. And you do not also have a system. So you neither have the controller in physical reality, you do not have the system also in physical reality. Both of them are software models. And you combine them and do a simulation and check whether your controller is working properly. That is what is called a software in the loop simulation. And you can then extend that to make a hardware in the loop simulation. Which is called, in short, SILS. Both these are used for controller prototype. So you develop your controller either by using a model of the system in the simulation, which we usually do initially, and then you again use the model of the system, but instead of the software controller, you plug in the hardware controller. It is also possible that you plug in the hardware controller with the hardware of the system, if that is permitted. So in either case, what is clear is we need a model. Of the system. So this is what is combining both systems as well as controls. So system model, we require, here you require controller model, these two will interact with each other. So I hope that introduction is clear. What you have is, in order to design a robust controller for a system whose parameters are not certain, for example, in the lift, you don't know how many people are riding that lift. You must require a controller which will follow the command exactly with certain technological specifications, like it should not overshoot, it should not oscillate, it should not miss the target, it should not take too much time. So these are our technological specifications or constraints. Within these constraints, you must be able to design a controller irrespective of what is the system parameters or various in system parameters, so that the desired objectives are met. That is why to design the controller either in hardware domain or in software domain, you first require a model of a system, and this model you will develop usually based on long parameter assumption. The control systems as such is a big field. It's very, very complex field. In your course, you will learn elementary control systems. I would say it is elementary control systems because if you ask your friends in electrical engineering department, this is like bread and butter for them. They do various higher levels of controls. So here you will only have half a semester course on controls. The idea is to give you a flavor of the field rather than complete details of control systems. If you develop any interest in that, then of course you can do further studies on control systems. Anyway, many of you have already participated in KITIs and such activities where you have used some kind of control, but most probably without knowing the details of the controller or the model. So in this course, formal theoretical details of developing these controllers will be provided. Maybe if you knew this theory before, you could have developed a better controller during your actual participation period. So I will just introduce some basics of modeling using Lagrangian and Hamiltonian principles, which you already know from your dynamics course. So it's just a refresher. So I will again go through those things very briefly, and then I will finish today's class, which again we will continue in the next week. So let me go for modeling. How do we model systems? So let me create a new tab. Modeling is a new tab. So you know how to create mathematical models of various systems. We know already some very useful things like Newton's equations, Lagrangians, and Hamiltonian mechanics. So these are the basic things we deal in mechanical engineering. You know already how to do them, so I will just go through them quickly. So let's take a spring mass system for brevity. So we draw free body. Let's say its velocity is x here, displacement. So you have here mx double dot pseudo force. Then you have here downward kx. We get mx double dot plus kx equal to 0. Let me make this little bigger dots. So that's the Newton's equations. If you write in terms of Lagrangians, so we write our Lagrangian in terms of generalized variables. So let us say we define Q, generalized coordinate, as x. Then Lagrangian we define as a function of, let's say, Q dot P is P minus B. We can add Rayleigh dissipation and other things afterwards, so let's not worry about that. So this, for this case, we will have Lagrangian is half m x dot square, that is kinetic energy, minus half kx square, and our equations of motion we know d by dt, these are whole derivatives, del L by del Q dot minus del L by del Q is 0. So Q dot we know is H dot. Right. So that will give me d by dt of mx dot minus minus becomes plus kx is equal to 0. So you note that this mx dot appears inside the derivative. So if mass is constant, then only we can bring it outside. So for dm by dt is equal to 0, we get mx double dot plus kx is equal to 0. So both these, let's call this equation number 1. This is, let's say, equation number 2. So number 1 and 2 are same. Second order differential equations or ODEs. So these are second order differential equations that you know very well how to derive these for complex systems. You must have done in your dynamics class. So we are not going into details of that. For example, Mach pendulum, simple pendulum, double pendulums, and so on. So let's go to Hamilton's equations. Okay. So before going to Hamilton's equations, let's come back to this Lagrangian equations. What we find here is Lagrangian is defined as a function of q, which is generalized coordinate, q dot, derivative of that generalized coordinate, and time. In mechanical domain, q is displacement, q dot is velocity. If you are dealing with angular displacement, then it is angular velocity, and you have time. But let's say you are doing Lagrangian for an electrical system. Then Q is charge, Q dot is current. Alright? Right. So these are mixed up in certain way, right? But they are completely different from the mechanical domain. In mechanical domain, it was displacement and angular velocity, whereas here it is charge and current. So there is no commonality between this. But let's go to Hamiltonian domain and let's try to find out certain commonalities. So in Hamilton's equations, as you know, we define generalized a variable P is generalized momentum. And Q is generalized displacement. So we have generalized momentum and generalized displacement. Interestingly, we can show that P dot or derivative of P with respect to time is effort. We know that integral FDT is momentum. That's post momentum equation. So derivative of momentum is effort. That is generalized effort, which in our case is force. And Q dot is equal to F is generalized flow. Example, velocity, angular velocity. I have written angle in short, current, etc. And in this generalized effort, we can put example force, torque, voltage, etc. So P dot is generalized effort, Q dot is generalized flow. So what are the units of P dot and Q dot? Its units Q dot vary according to domain. Example, mechanical, electrical, thermal, etc. So this P dot and Q dot, they vary. But this is in capital. But P dot dot product with Q dot, that is E dot F. What is this? Effort into flow. This is power. Its unit is watt or joules per second in all domains. So this is very important that the unit of power is domain independent. This is not dependent on domain. Whereas individually, P, Q, P dot, Q dot, they may have different units, different connotations in different domains. P dot into Q dot or effort dot product with flow is power. Its unit is same. So let us now come back to the analogy. In our country, we have people having different culture. We have people speaking different languages, people having different religion, etc. If somebody who is speaking Hindi goes to a village in Tamil Nadu and speaks only Hindi, nobody will understand what that guy is speaking. Likewise, a Tamil guy comes and speaks to me in Bengal, I won't understand, I won't make out what this person is speaking at all. Because we have no commonality between our languages. Even if that person writes down something in Tamil, I will not understand because the scripts are completely different. Likewise, the Hindi-speaking person writes down something in Hindi, the Tamil guy will not understand. Scripts are different. We have completely two distinct varieties of scripts. As we understand, Indo-Aryan languages and Dravidian languages. These are completely different. So, in order to pick a common language, sometimes we say, okay, Hindi is our national language, but some people do not agree to that. Some people say, okay, English should be our common language. Then neither English nor Hindi have any commonality with any kind of South Indian language. So, in order to interact together in a perfect manner, what we require is a common language. Only if there is a common language, there will be problem in interaction. Likewise, if you look at these different systems have different kinds of units, different kinds of coordinate systems. In mechanical systems, we put coordinate systems X, Y, Z. This is our coordinate system, say. This is our mechanical coordinate system. In electrical domain, what is our coordinate system? We say current like this is positive, let's say I1. Then let's say you have something here I2. Then here this is I3. Maybe it's this way I have taken positive. So some direction I have assumed that is my positive direction, that is my coordinate system. So every domain coordinate system is changing, every domain variables are changing. That creates a big problem. Therefore, this power is an interesting quantity which is common across all domains. So, what this Hamiltonian formulation does is basically it unifies different energy domains. So, Hamiltonian formulation unifies energy domains. The common currency exchanged is power. So even if you have different energy domain, what is being exchanged between them is power. Power is the thing that will be exchanged between electrical to mechanical to thermal or other domains. And Hamiltonian formulation is a means to represent that dynamics. So that is why in comparison to Lagrangian mechanics, where those things were not appearing, momentum and general flow. Here, though flow was appearing, momentum was not there. Here, explicitly these relations. So we define some things, E and F, that is P dot and Q dot are called power variables. They are called power variables so that